Hi everybody, welcome to another video in this week's math section 5.2, strong induction and well ordering. Strong induction. Strong induction is the way to prove where we verify the first one, the predicate is true when n equal to 1. That's exactly like what we did with the induction, but the inductive step is different. We assume that it is true from 1 to k, and from there we show that it is true for k plus 1. So regular induction, assume that it is true, p of k is true, show that it will be true for p of k plus 1. Strong induction, we assume that it is true from 1 to k, and then we use that to prove that it will be true for k plus 1. Right, and it's called the second principle of mathematical induction, or the complete induction. So in the example of climbing a ladder, if we reach the first step and assume that we can reach k step, then we can show that it will can go to the next step. So we assume that it's true from 1 to k. Alright, so that's what we have here. Assume that it's true up to k, and we use that to prove that it's true for k plus 1. Alright, let's look at this example. Show that if n is greater than 1, then n can be written as a product of primes. So we'll write the statement we need to show p of n, and we say n can be written as a product of prime. Because n here is greater than equal to 2, because greater than 1. Right, so the step 1 is the basic step. The basic step that we show that is true from the first values. So p of 2 is that 2 can be written as a product of prime. And it is true, because 2 itself is a prime. Right. Now, go to the second step, the inductive step. In this strong inductive step will be assume that is true from p2 to pk. Right? Now we need to show p of k plus 1 is true. Right. Now to show that, it's actually rather easy. So first, if k plus 1 is prime, then itself is a prime, then it is the product of prime, so this is true. Now if k plus 1 is not prime, then it must be a product of two numbers. Now, it must be a product of two numbers. By the way, a and b have to be, when a and b have to be greater than 2. because if A is 1, then B is K plus 1, and I would say it's not prime, so it have to be A and B greater than or equal to 2. Now, if that is the case, then A and B have to be one of those. I mean one of those from 2 to K. So, and so A and B less than K. Less than or equal to K. Doesn't matter. Meaning A and B are product of prime. Because we assume that from 2 to K, all of them are product of primes. So A and B are also product of primes. And if A and B are product of prime, so K plus 1 is equal to A times B, a product of prime and a product of prime. It is also a product of prime. So that's actually all. That's all. So the fact that we assume that is true from 2 to K, all of those numbers from 2 to K are product of primes. So that including A and B. So a product of prime times a product of prime is a product of prime. So K plus 1 is also a product of prime. Right. Next, prove that every amount posted 12 cents or more can be formed using 4 cents or 5 cents. Now, we have greater than or equal to 12. So we say it. What we need to show is that can be formed using that n can be constructed or can be formed using 4 cent and 5 cent stamps. Right. And for here n is greater than or equal to 12. Now, basic step. Basic step. We start with the smallest possible, which is P of 12. Right. Now, if it is 12, how we construct using 4 and 5? Well, we just have 4 plus 4 plus 4. And so it is true. Right? Yeah. So we can construct 12 using the 4 and 5. Put 4 and 5 together. Doesn't matter how many we have for 4 or 5. That's what we have. Now, the inductive step. So we assume that from 12 to K is true. Let me write it. Assume that P of 12 on the way to PK are true. Need to show that P of K plus 1 is true. For this one, a little bit different. We need to show for a few more. Alright, P of 13. We know P 12 is true. Now P of 13. 13 can be written as 4 plus 5. So it's true. P14 so that is true. P15 that also true. Right, so we have 4 cases, 12, 13, 14, 15, those are true, right? Now, of course, we can do a few more here, but I think that will be enough. Now, what we focus on is the case of P of k plus 1. Now, we can construct as follows. We can write P of k plus 1. K plus 1, you can write that as k minus 3 plus 4. Right? Now, remember we have 4 cases for 12, 13, 14, 15. Right? So the 16 is equal to the 13. The 16 is, if we need to solve for 16, it's going to be equal to the 12 plus 4. Right? And the 17 is equal to 13 plus 4. So we have the first 4 cases. And then so the next one, starting from the 5th, can be written as the P4. So for example, if we can say P of 16 is equal to P13, 16 is equal to 13 plus 4. And that is also true. So we know that this can be, it's true. So plus 4, so that's also true. Yeah, because we have the first 4 cases already. And we assume that it's all the way up to k. So P of k minus 3 is true. And therefore plus 4, P of k plus 1 is also true. So that's all we have. So we have to solve for 4 cases. And the next one, we just add a 4th piece. And then the 17, we're going to use the 13 plus 4 and the 18, 14 plus 4, and then so on. Because it's only true for 14, it would true for 14 plus 4. And that's how we do the strong induction. So we assume that is true from 12 to k. Right, that's strong induction. Next, we have well ordering. The principle of well ordering is that every non-empty set of non-negative integer has a least element. Well, that's too simple, right? It has a smallest number, have the minimum least element. If everything is order, you can say something is greater than the order, and then you can you have the smallest one, right? So a set is well ordered if every subset has a least element. That definition. And n is well ordered under less than or equal to. So we can order them. The set of finite string over an alphabet using, okay, that's another example. Next, using the well ordering property to prove that the division algorithm, which state that a is an integer and d is the positive integers, then there's a unique Q and R such that this, right? So now here we can just roll things around and we set a equal to that. So we can say R is equal to a minus dq. Right. Now we let the set of all of this a minus dq. Of the form I'm just going to say R minus dq. Of course, we can choose. By the way, what we have here is A is given, and D is the divisor is given. So we let S be of the form A minus DQ, right? And we can make this as this set is non-empty because we can choose every time we choose a Q values, we have one number, right? So S is non-empty. Because we can choose the quotient being arbitrary. We can choose that arbitrarily. Right. Next, by the well-ordered principle, there has to be the list, and let that be list element be R. Well-ordering property. There is a list element of those A minus DQ. Okay, so there's a list element R equal to D A minus DQ, right? And then here the kicker, we have to show that R is less than, only it's the list of them, but they have to be less than D. And so if it is the list, now we say that if it's the list, then it have to be less than D. Why is that? Because if it's not, if R greater than or equal to D, we can choose the order R. This is not derivative of the order R equal to A minus D Q plus 1. Meaning that if R is not the smallest, we can increase the quotient one more. And that equal to A minus DQ minus D. And that have to be greater than 0. And A minus this, so that's going to be R. Right. So as you see, we have the smaller element satisfying this. Right. Bottom line is, if the remainder is not less than the divisor, we can increase the quotient. And that increase the quotient, we still have R minus D greater than 0. Right? So we can choose something smaller. And if this is not the smaller, we can always choose something smaller until we cannot do this anymore. Right? So in that case, it have to be less than D. And of course, have to be greater than or equal to 0 as well. Yeah. Yeah. So we write like this in the form of non-empty, and we choose that so that it will be only positive and non-negative. I'm just going to say of non-negative just to be safe here. Of course, we can choose the quotient, we can choose Q so that R is negative, but we will not choose that. We choose only Q, so to make it all of this result positive. And if all of them non-negative, so it's non-empty, so there's a list element. And we have to say it's less than it, because if it's not less than, we can choose another smaller one by increase the quotient, and we just keep increase the quotient when we cannot increase it anymore. There will be some number that is smaller than it. So with that, we say there is a quotient and R so they are Q and R such that R less than D but greater than or equal to 0. Right, so that is using the well ordering property to show that to show the division algorithm. And with that, we finish section 5.2. As always, thank you for watching and see you in another video in Discrete Math.